Welcome to all. So, let us start the lecture. So, now we come to the crux of the thing. Okay. Now, we will try to see whatever we have learnt till now, whatever we have learnt in the single degree of freedom analysis system, we will be using this thing to formulate what is known as the equivalent static load and use it even if we do not understand the dynamic analysis to the greater extent. Okay. So, I will try to summarize the single degree of freedom system analysis again one more time, and then we will see how this thing we can apply as an equivalent static load factor. Okay. So, what we did was we started with a physical system, okay, which was having a external force F of t. Okay. So, we choose the degree of freedom at the center, because we know if this load is applied at the center, okay, the maximum response will be occur at the center. So, our chosen degree of freedom y was x equals to L over 2. So, this was my chosen degree of freedom, and correspond to this degree of freedom we are choosing this mode shape. Okay. So, this was our choice of mode shape. Okay. So, we choose the mode shape, we choose the location of the degree of freedom. From there we made our shape function. So, shape functions, what we did was we used the same system. Okay. We applied a static load P, okay, and we calculated the deflection profile. Okay. So, this was the deflection profile. So, we wrote down the deflection profile here, or the deflection equation, and denominator also we wrote down the deflection equation, and we evaluated the deflection equation at x equals to L over 2. Okay. From there we calculated my equivalent mass, my equivalent stiffness, and the forcing function. So, we integrated over the entire length, we put the mass per unit length, then my shape function squared, integrated over the entire length. So, I got my equivalent mass, equivalent stiffness same way, EI here we are keeping it as the constant. Okay. And forcing function. Okay. So, that way we calculated my mass, stiffness, and the forcing function. If we want to calculate the damping, we can calculate damping as a function of mass and stiffness. Okay. So, from here I got my equivalent single degree of freedom system. Okay. Okay. And this is my chosen degree of freedom, which corresponds to the deflection at the center. Okay. So, once I have my chosen degree of system and I have my equivalent system, we calculated we wrote down the equation of motion, and from the equation of motion we calculated the total response of the system. Okay. From here, from my equivalent single degree of freedom system, we wrote down the equation of motion, and from the equation of motion we wrote down the total solution, that is this corresponds to the deflection at the center. So, x equals to x particular plus x complementary or x steady state plus x transient. This will be the signature of the system or signature of the system in free vibration, and this guy corresponds to the signature of the system corresponding to a forcing function. Okay. So, this will be a function of forcing function and the stiffness, and this will be a function of omega of the system and the associated damping. Okay. From there we calculated x and denoted it as a function of x static, okay, then omega of the system and the damping ratio. Okay. So, this much was the single degree of freedom approximation method, where we calculated the total system response. Okay. Now, we will look the thing in a reverse way. Okay. Now, we will again analyze this system, but in a reverse way. Okay. So, we again take our physical system. Okay. We will again take our physical system. Let us say we have taken our physical system. Okay. And this was the response of the system. Let us say we are again analyzing the system for the same scenario, and we are trying to calculate the maximum response. Okay. The maximum response u max. Okay. So, if I differentiate this thing, equate it to 0, I can calculate the maximum response. Okay. I can get the maximum response here. Okay. So, let us ignore the cause, what has caused this system to vibrate and displace for this u max. Okay. Let us look into the effect only. We are just looking into the value of u max. Okay. So, when we started this problem, the u max was caused by due to an external applied load. Okay. Due to a time varying external applied load. Okay. Now, we are arguing that this has been caused due to a static load. Okay. We put a equivalent static load, and this load caused this u max. Okay. So, we are trying to change the dynamic system into a equivalent static system. Okay. So, we will keep u max. So, in order to get my u max, the value of this equivalent static load should be stiffness times u max. Okay. So, this is the concept of the equivalent static load, okay, where we ignore the effect, where we ignore the cause, and we take the effect only. The effect is, let us say we are looking into the maximum displacement. So, we take the effect only, and we say that the effect has been caused by an equivalent static load. So, we took the equivalent static load, and we know how to calculate the equivalent static load using the stiffness of the system times the maximum displacement. Okay. So, this is the mathematical relationship of the equivalent static load, okay, where F equivalent equals to equivalent static load factor times the F dynamic. Okay. It means that ESL is coming from u max divided by u naught, okay, and u naught again was a function of F naught divided by k. Okay. Okay. So, this is how we are getting the F equivalent. Okay. For different type of loadings, okay, for harmonic loading we call it dynamic magnification factor. For transient loading, it will depend upon the load duration and the system properties, but basically at the end of the day we are saying that the equivalent static load equals to F dynamic times the equivalent static load factor, which is nothing but my ratio of u max divided by u naught. Okay. So, the philosophy here is we convert the dynamic analysis to a static analysis. We use the static analysis tool. Once we know the equivalent static load, okay, now we come back to knowledge of our static analysis. We can apply the static analysis and methodology whatever we know, and from there we can calculate the forces, we can calculate the stresses, we can calculate the bending moment, shear force, strain, we can calculate the stresses, and we can start the design process. Okay. This ensures a conservative design. Okay. So, what we have done is that even if we lag in the knowledge of our dynamic analysis, what we can do is that we can convert into an equivalent static analysis, and from the equivalent static analysis we can formulate the equivalent static load, and from there we can do the design that we need. Okay. Okay. So, there are different methods, okay, to calculate the equivalent static load factor. We can take the maximum dynamic displacement divided by the static displacement that I showed earlier also, basically u max divided by u naught. Okay. We can took the root mean square of the displacement also. Okay. We can calculate the equivalent static load factor based on the equivalent strain energy. Okay. and we can use different factors also depending upon the time ratio. Okay. So, in different books or in different methodologies, different type of equivalent static load factors are being used. Okay. And most of the time what we do is that we try to calculate using the maximum ESL factor. Okay. That will give us a conservative design. Okay. See we always go for a conservative design. Okay. So, we will always try to calculate the maximum ESLF factor. Okay. But remember one thing, why we are trying to use a conservative design? Because remember what we have done when we started, we just took only 1 degree of freedom. Okay. We ignored the effect of the higher degrees of freedom. Okay. So, it means that Umax, whatever we are estimating Umax, that is Umax is always less than my U actual. Okay. So, there is a big approximation inbuilt out here. Okay. So, that is why even though we are trying to use a conservative design, but we are trying to approach U actual as large as possible. Okay. So, that our design is accurate. Okay. So, this is the approximation. Okay. And we always try to go and achieve the U actual. Okay. Though we know we are ignoring the effect of the higher modes. Okay. Again the same thing denoted in terms of equivalent static load factor. So, here we have what we are showing is that we are using the dynamic increase factor, and same graph we are showing using the equivalent static load factor. So, the same resonance characteristics will be followed. Okay. Here what we are trying to do is that we are trying to give some small examples, so that we can start off and get some hands on knowledge of the analysis of the single degree of freedom system. So, again a mass is being taken, stiffness is being taken, damping ratio is taken, and a harmonic force is being applied to the system. So, the steps in solving this equation is we calculate the natural frequency of the system, we calculate the dynamic magnification factor, we calculate the frequency ratio, we calculate the maximum steady state response phase angle, and then we calculate the equivalent static load factor. Okay. So, a step by step solution is given here, which can be used to practice. Okay. So, we calculate the natural frequency, okay, root over k over m, 1 over this one will give my time period, frequency ratio, okay, the ratio between the applied frequency versus the natural frequency, dynamic magnification factor. Using the same equation we can calculate the dynamic magnification factor, and then we can calculate the maximum deflection. Okay. So, here you can see we can, if we know the dynamic increase factor, okay, if we know the dynamic increase factor, and we have the knowledge for calculating the static response. So, if we multiply both these things, we can directly calculate the maximum static loading, maximum dynamic loading. Okay. So, here we have done nothing, we have calculated the dynamic increase factor, okay, multiplied by U static and calculate the U dynamic. Okay. So, here nowhere we have solved the equations. Okay. We have solved the single degree of freedom equations, we have just used the inbuilt equations, okay, that can be used by the practicing engineers or the undergraduate students who have less knowledge of this dynamic analysis. Okay. And this can be very easily used in the design offices. So, additional results, we can also look into the phase angle variation, equivalent static load factor. Again, if we multiply the loading, okay, with the dynamic loading factor, we can calculate the equivalent static loading. Okay. Once we have the equivalent static loading, okay, once we have the equivalent static loading, okay, we can calculate the bending moment, we can calculate the shear forces at any given sections. Okay. We can if we take this, okay, so we can calculate the bending moment, axial forces, shear forces. Okay. We can also take any chunk out here, okay, and we can calculate the stresses, okay, and then we can use these values for design of the system. Okay. So, what we have done is that we have reduced the entire system, did a single degree of freedom analysis, then calculated the equivalent static load, and then we calculated the bending moment, shear forces, axial forces, we calculated the stresses and strain, and then we can use these results to design this system or analyze this system as the case may be. Okay. So, we have simplified the dynamic analysis to an equivalent static analysis. Again, one more problem is been given. So, these problems can be used as a practice problem. Different type of loading is been given. In the first case, we have the harmonic loading applied. Here we have a step force applied. Okay. So, different types of loadings are been given. Okay. So, that the students can practice on this thing. Okay. So, again frequencies are being calculated, the response of the system to the step function is been given. So, maximum time period to achieve this thing has been given. Okay. So, maximum value of the displacement is being calculated out here. Okay. After that, we can calculate the maximum equivalent static load factor, which is again U max divided by U naught. Okay. And from here we can see that for certain loading the approximate value for ESL is 2.0, but the actual ESL that we are calculating is 1.875. Okay. So, our calculations are more accurate. Okay. So, if it would have been the other way around, then there would have been problem, but we are not exceeding 2.0. The actual one is less than 2.0. It means that whatever we are calculating, we are under the conservative phase only. So, engineering calculations, dynamic application factor is significant. Okay. Damping reduces the peak responses and the quasi-static gives conservative estimate. Okay. Whenever we are designing or whenever we are analyzing, we have to be on the conservative side. This has been shown by this analysis. Okay. Okay. Again, third problem is been given. So, here the forcing function is a random vibration with the frequency range changing from 5 to 5000 hertz. Same way we will calculate the natural frequency, we will calculate the frequency ranges, and we will try to calculate the peak responses. Okay. So, this one will be given as a practice work, and let us try to see this in a practice work and see what are the things coming up. Okay. So, now we will try to see an overview of the things that we have analyzed. As far as the design consideration goes, to avoid the resonance, the operating frequency should be in this range. Okay. Safety margin will also depend upon the damping level, and we will have to consider the frequency of the vibrations that are going to occur. Okay. So, the damping requirements 0.02 for steel structure. If the resonance is more, then we need higher damping. Okay. So, let us say in certain cases the external applied frequency and the frequency of the system are going to match. Okay. But if they are going to match and if there is no damping, okay, then we will have resonance. Okay. And the response will go out of bounds. Okay. So, in order to avoid this situation, okay, where we are stuck up with this equivalence in the frequency, then we will have to increase the damping, so that the total response, okay, the total maximum response of the system is under permissible limits. Okay. So, equivalent static load factor application, it uses conservative values for the design, it considers the actual loading effects, and it also accounts for the multiple load cases. Okay. Some typically used loading factors are 2.0 for impact loading, for seismic loading it is 2.5 to 4, and for wind gust it might be 1.3 to 1.5. So, these are some conventional estimate. Okay, these are conventional estimate, but now using this analysis we have been given the tool so that we can calculate the actual ESL. Okay, we can calculate the E actual. Moving ahead. So, this is a summary of the different types of loading: static loading, quasi-static loading, and dynamic loading. Static loading, it is a constant type of applied loading. Quasi-static loading, slow and gradual loading. Dynamic loading, sudden and rapid loading. Strain rate almost negligible in case of static loading, 10 raised to the power -2 in case of static loading, and for the dynamic loading it starts from the 10 raised to the power -2 and it can go as high as 10 raised to the power 5 or 10 raised to the power 6. Okay. Inertia effect ignored in the static loading case, negligible in the quasi-static phase, and in case of dynamic loading it plays a very significant factor. Kinetic to internal energy ratio almost 0 for static loading, some values for the quasi-static loading and significant for the dynamic loading case. Analysis type: static equilibrium loading for the static load case, static equilibrium but time varying loading. Okay. For the dynamic loading we have to do a fully dynamic analysis, but some sort of getaway is also available, like we just saw using equivalent static load method. Okay. So, this is a roundabout of the dynamic load analysis. If we do not want to do the actual dynamic load analysis, we can also use the conservative equivalent static load analysis and try to analyze and design our system. Material rate effect, none available in the static loading case, almost 0 in the quasi-static loading case, and this becomes a very important factor for the dynamic loading case, because the stiffness of the system and the strength of the system goes up, but the ductility goes down. So, the material strain rate effect has to be taken into consideration here. Stress waves are absent in case of static loading and quasi-static loading, and they very much well quantify the responses in case of the dynamic loading. Typical duration, this is a very long applied loading. Again, the loading time and the natural time period ratio is very high. Here the loading is applied very rapidly. Some examples of the static loading: dead load, gravity load, any type of static load that we test. Quasi-static loading, material testing, settlement, forming. Dynamic loading examples: impact, blast, earthquake, crash, wind loading, and so on and so forth. Computational cost: static loading, it is the lowest cost, because most of the time we have to solve for the externally applied loading divided by the equivalent stiffness. Quasi-static loading also some sort of externally applied load, stiffness, and some formation of the mass if applicable. And this is a very computationally expensive task, because not only we will have to calculate for the externally applied loading, stiffness, mass, but we also have to take into account different type of failure mechanism, change in the material behavior, and the other factors. So, computationally this is very expensive. When to use? When the static load is constant, we can approximate it using a static load factor. Quasi-static, when the load is slow, for example in test of slow material testing, and the rate effects are negligible, we can apply the quasi-static loading. Okay. Dynamic loading, when the load is rapid, the inertia effects plays a significant role and the rate effect plays a significant role. Okay. So, these are the distinctions between the three type of loadings. Moving ahead, so whatever we have learned, how to use this thing in a design or analysis office. Okay. So, what we are trying to do is we are trying to calculate the maximum response of the elastic single degree of freedom analysis for different type of loading. Okay. So, what we will do? We have our system. Okay. Let us say we have system 1, system 2, system 3, system 4. Okay. And system 1, 2, 3, 4. Okay. So, this system is denoted by my frequency and damping. Okay. For the sake of our argument, let us remove the damping. Okay. So, this system can be denoted by the frequency, frequency 2, frequency 3, natural frequency 3, natural frequency 4. Okay. And let us say we have a external force applied. Okay. So, external force P1, T1, P2, T2, P3, T3. So, the maximum response of the system, okay, the maximum response of the system x max will be a function of omega n, the value of P and value of T. Okay. So, here omega n is represented by Tn. Okay. Omega n equals to twice pi Tn. Okay. And the loading, the duration of the loading is represented by T, and the dynamic load factor is nothing but my U max divided by U naught. Okay. So, what we have done is that we have changed the system Okay, we have changed the value of omega, and we have changed the value of p, we have changed the value of t, and here we have varied the value of t divided by Tn, and this way we have varied the value of p, okay, because u naught is nothing but p divided by k. So, what we have achieved is a comprehensive graph of the value of u max divided by u naught, okay, by varying the system parameters omega n and by varying the load parameters p. Okay. So, now let us say we have been given one case where we have been given a value of, say this has a particular m, a particular k, okay, m1 k1, okay, and the forcing function is, let us say, f1 t. Okay. So, if I was asked to calculate my u max for this system, here what I need to do is that, and f1 is f1 t1. Okay. So, what I need to do is that I need to calculate omega n 1, which is root over k over k1 m1. Okay. Then I, from omega n 1 I calculate Tn 1. Okay. I have my value of T1. So, then I calculate the ratio of T1 divided by Tn1. Okay. Let us say this is a number A1. So, A1 I choose here, let us say it is 0.5. Okay. So, I come to this point 0.5, okay, and I go up, find where it is cutting this graph. Okay. So, this corresponds to a value of, let us say, 1.4. So, I got a value of 1.4. So, u max divided by u naught equals to 1.4. So, u max equals to u naught times 1.4. The value of u naught is nothing but f1 divided by k1 times 1.4. Okay. I know the value of f1, I know the value of k1, and hence I can calculate the value of u max. Okay. Once I have the value of u max, I can take the same system. I have the same system. Okay. My equivalent static load becomes f1 times u max. Okay. So, this equivalent static load I can put here, and from there I can calculate my bending moment, shear force, axial force, stresses, strains, whatever is the requirement. Okay. So, I can design the system as well as I can analyze the system, okay, as the case may be. Okay. So, this graph, okay, this graph can be used as a replacement for the, instead of doing the entire dynamic analysis, I can use this graph in a office and calculate the response of the system and use it for the design or the analysis as whatever requirement has been given to me. Okay. So, this is a workaround for the actual dynamic analysis. So, this thing can be made for the other type of loading also. In the first case, we saw we had a triangular type of loading. In the second case, we have a rectangular loading. Third case, we have a gradually applied loading. Okay. So, for each and every load case, we can make this graph. Okay. We can make this dynamic load factor graph and use this for the design and analysis purpose. Okay. So, different in different books, in different literature, we can easily find these graphs. Okay. Some of the graphs that are available readily are in TM5 1300. Okay. Here we can find different types of graphs out here. Same is also available in UFC code also, okay, or in any other dynamic design books. We can find the same graph. We can use the same graph even if we do not know how to do the actual dynamic analysis, and we can, using this graphs, we can analyze the system and we can design the system. So, to summarize, what we have done is that we have introduced a concept of equivalent static loading. We took a actual system, we took the single degree of freedom approximation of the system, we calculated the maximum response of the system, and using the maximum response of the system, we introduced a term called equivalent static load factor, and from the equivalent static load factor we can calculate the equivalent static load, and from the equivalent static load we can use the knowledge of the static analysis, and we can calculate the applied bending moments, we can calculate the bending moment, shear forces, axial forces, stresses and strain in the system, and we can use these values to either analyze or design of the system as the requirement may be. So, this is a very powerful and effective tool that can be used by BTech students, MTech students, PhD students as well as the practicing engineers, where they are faced with this type of dynamic loading. Okay. And this type of graphs are readily available in any of the available literature. Okay. So, I conclude this lecture today. Thank you.